the following synthesis could be accomplished. So here you want to just reduce an ester but not the ketone. So any type of hydride reagent you would use would reduce both the ketone and the ester. So how would you accomplish this? Well, the answer is you would use a protecting group for the ketone. So first you would protect the ketone as its acetal. So you would use, for example, this diol. You could use other alcohols and remove water to favor acetal formation. Now that you have the acetal, you can then use LAH to selectively reduce that because LAH won't touch an acetal. And then when that's accomplished, you can add acid and water to remove the acetal and get back to your original ketone. So these are the three steps. So one would be acetal formation to get to this product. Two would be lithium aluminum hydride reduction, which would get you to that primary alcohol, but your acetal would still be formed. And then acid and water would remove the acetal and take that back to its starting ketone. If you noticed in that mechanism for the acetal formation, we went through an intermediate called the hemiacetal. Those are generally difficult to isolate as equilibrium either favors the starting aldehyde or ketone or the ending acetal based on the conditions used. However, cyclic hemiacetals can be isolated. A cyclic hemiacetal is possible when a compound contains both the carbonyl group and a hydroxy group. So here, this would be adding to the carbonyl. Cyclic hemiacetals are very important in carbohydrate chemistry. For example, glucose can exist in either its open chain form or in its closed chain form where it is a cyclic hemiacetal. So here's the hemiacetal. So there's the OH, and this is the OR portion. Now it's time for an organic chemistry joke break. Take a look at this and let me know if you get it. Moving along to nitrogen nucleophiles. Under acidic conditions, aldehydes and ketones react with a primary amine. Remember, that's an amine, a nitrogen with two hydrogens attached, to give what's called an imine. And those two words sound a lot alike, amine versus imine. So just be careful that you know which one you're talking about. The imine has a carbon double bonded to a nitrogen. An amine is a nitrogen with three groups attached to it. And this reaction requires acidic conditions to work. So here's the mechanism. In this, an amine is a good nucleophile, so we don't need to protonate the carbonyl oxygen first. So the nucleophile is going to attack the carbonyl and break the pi bond. In the second part, the oxygen atom is going to get protonated by the little bit of acid that is present in the reaction. In the next step, the conjugate base of the acid is going to remove one of the hydrogens from the nitrogen atom to get rid of that positive charge. Now we have this intermediate in this green box known as carbinolamine. Now the next step is we want to protonate the OH group. So that lone pair is going to grab a hydrogen from the acid. And now we have water, which is a good leaving group. So here the nitrogen lone pair will donate in and form a double bond with that carbon, simultaneously kicking off the good leaving group of water. Then we're almost done. We get to this protonated imine. So one more proton transfer removes the hydrogen from the nitrogen, and you get your neutral imine product. Now, even though this is under acidic conditions, protonation of the carbonyl is not the first step as you might have imagined. In fact, amines are such good bases that they actually react with the acid first to form an ammonium ion. And then that ammonium ion is the acid catalyst used in the reaction. And then this ammonium ion is not acidic enough to protonate an aldehyde or a ketone, but it is acidic enough to transfer a proton to the negatively charged oxygen in the second step. For imine formation, the pH has to be right around 5 or the reaction is too slow. If you have a higher pH, there's not enough acid to catalyze the reaction, and if you have a lower pH, all of the amine would be protonated and none would be available to act as a nucleophile to attack the carbonyl. If you react an aldehyde or a ketone with a secondary amine, you get what's called an enamine. So here you have a carbon-carbon double bond, that's where the En of the word comes from, and you have an amine functional group. This reaction also requires acidic conditions, and it's almost identical in mechanism to the imine formation except for the last step. So here, just like with the imine, we have nucleophilic attack on the carbonyl, followed by proton transfer, and another proton transfer. It's getting to that same intermediate, so everything here is identical to the imine mechanism. Then we're going to protonate the OH because we want to convert it into a good leaving group. Then we're going to use the lone pair on the nitrogen to kick off water. And then this final step is the only thing that's different. Because there's no hydrogen on the nitrogen with the secondary amine, we can't remove one of those R groups. So we're going to remove hydrogen on an alpha carbon, and that's going to create that carbon-carbon double bond in the enamine. So here's a summary. If you start with a ketone or an aldehyde, if you have a primary amine, you end up with an imine, carbon-nitrogen double bond. If you start with a secondary amine, you end up with an enamine. Okay, now let's try making imines or enamines. So you make an imine when you have a primary amine. That means you have a nitrogen with 2 hydrogens attached to it and a carbon group. You make an enamine when you have a secondary amine. That means a nitrogen with 1 hydrogen attached to it and 2 carbon groups attached. So pick any of these reactions and draw either the imine or the enamine product, depending upon the type of amine that it's reacting with, primary or secondary, and then take a picture of your answer and paste it into the chat. If you're having trouble reading this on the video, you can go to the slides in Canvas and look at the slide with all the reactions shown. There is a reaction called the Wolff-Kishner reduction, which is a 2-step synthesis. And in this, you convert a ketone to an imine using this particular reagent called hydrazine. And it's going to react like a primary amine. And then in the second reaction, you use potassium hydroxide and water, and it will take that imine to just a CH2 group. So the mechanism of the first step is just imine formation, which we've already seen. The second step is shown here. So the strong base, the hydroxide, is first going to deprotonate the nitrogen with the 2 hydrogens on it. And then we are going to draw resonance structures. So if we look at this resonance structure, there's a negative charge on that carbon. We're going to protonate that with water. And that takes us to this intermediate shown here. Then another equivalent of base will come in and deprotonate that nitrogen again. And now we get to this intermediate. That negatively charged nitrogen atom will use its lone pair to form a 3rd bond, so to form a triple bond, breaking this carbon-nitrogen bond. And in the process, nitrogen gas is expelled. So nitrogen is a fantastic leaving group. So we end up with this carbanion, which then gets protonated by water. And now you can see what you started with here, we've converted that to a CH2 group. So having looked at a lot of acid-catalyzed mechanisms, note that under acidic conditions, reaction species should either be neutral or have an overall +1 formal charge. If there's a +1 and a -1 charge in the same molecule, overall it's neutral because they cancel each other out. But you wouldn't want the reaction species to have an overall -1 charge. Acetals are hydrolyzed with aqueous acid to yield the starting ketone or aldehyde, and it's simply the reverse of the acetal formations. And this will only happen under acidic conditions. If you try to do this with base, there is no reaction. And here is the mechanism of the hydrolysis. So we're in acid. First thing we're going to do is protonate one of the oxygens of the acetal. And now we've got a good leaving group. So the other oxygen, its lone pair is going to come in and form a double bond with the carbon, kicking off alcohol. And now we have this intermediate. So now water is going to attack that carbonyl carbon, breaking the pi bond to get to this protonated hemiacetal. Water will do another proton transfer. And now we are officially at the hemiacetal. So this is just the reverse of the acetal formation. Now we're going to protonate the other oxygen. So now we protonate this oxygen to get to this intermediate. And now we have a good leaving group, and the other oxygen lone pair comes down, forms the double bond, kicking off the alcohol. And now we have the protonated carbonyl, so one more proton transfer gives us the starting ketone. And you may ask, well, why do I, like for example, let's look at this hemiacetal. Why did I protonate this oxygen and not that oxygen? Well, the answer is both are occurring because everything is in equilibrium. But if you protonated the OH oxygen, that would have given you the previous step. That would have given you the previous intermediate. So yes, all things are happening and it's going back and forth and equilibrating through all of these steps. But when you're drawing a mechanism, you want to draw steps that move you forward to the product. So if you had protonated this oxygen at that stage, that would have taken you backwards in the mechanism, not forwards. Hydrolysis of imines and enamines also undergoes a very similar mechanism under acidic conditions, which is essentially just the reverse of their mechanisms of formation. Let's wrap this up with some questions. The molecule shown here is an example of what? An alcohol, an aldehyde, a ketone, or a phenol. What is the correct IUPAC name for the following? Notice the double bond in this compound. Is it E6-chloro-2-hexenal, Z1-chloro-4-hexenal, E1-chloro-4-hexenal, or Z6-chloro-2-hexenal? Here, predict the product of the following reaction. So you've got a ketone, you've got acid, and you've got this amine. Notice that's a primary amine. Finally, predict the product of this reaction. So we've got two equivalents of methanol and acid. What will the product be? That's it. Thank you for watching.